A very good afternoon to everyone present here, and I warmly welcome you all for the 14th day of online gate training program 2022.
A very good afternoon to everyone
Today
present here.
we have two sessions. The very first lecture is going to be delivered by the very well known person in the field of environmental engineering, Dr. Shilpa B S. The topic is water quality and treatment. Dr. Shilpa B S is an associate professor in the Department of Civil Engineering with 19 years experience. She is actively involved in teaching water treatment engineering, solid waste management, and environmental engineering lab. She'll be speaking on the fundamentals of water quality and treatment. A very warm welcome you, madam.
Thank you, Manoj sir.
And with this, I request you to kindly take over the session. Thank you, madam.
Thank you, sir. Dear participants, welcome you all to the second session, which I will be dealing with the water treatment. So let me share screen. Okay, hope screen is visible, Manoj sir. Avinash sir?
It is visible, ma'am.
Okay, thank you. So welcome you all to the second session on exclusively which I will be dealing with the water treatment. So my presentation outline goes like this. So I will be dealing with the water quality index initially, then I will go with the water treatment, unit operations and the processes, then the water treatment methodologies, and then the water distribution system we will be studying in this particular session. So let us start with the water quality index. So water quality index is a means by which the water quality data will be summarized for reporting to the public in a consistent manner. Okay, usually the public will not be aware of the water quality parameters, so it will be represented in the form of a single number or a rating, so by which the public can be aware of what will be the quality of that water, whether it is suitable for use or not. Okay, so we can say the water quality index is defined as the rating that reflects the composite influence of a number of water quality factors on the overall quality of water. And usually this water quality index, it is a means parameters that we are considering. Maybe we can consider the imported 4 parameters, or we can consider 6 parameters or 8 parameters, so depending on the scenario. So large amount of the water quality data will be considered, summarized in the form of a simple terms, so that can be reported to the management or to the public or the policy makers, so which will help them to take a decision in a considered manner. So advantages of this water quality index, it will going to represent the measurements of a variety of the variables in a single number. Okay, we need not see the each and every parameter. So that single number will be going to tell about the quality. And as per the practice, it was found to be very effective tool to communicate the information on the water quality to the citizens or the policy makers, and then to implement the water quality monitoring or the improvement programs in the society. So coming to the methods of assessing the water quality index, actually there are 4 methods which are usually followed to express the water quality index. One is the National Sanitation Foundation Water Quality Index, then Canadian Council of Ministers of the Water Quality Environment Water Quality Index. The third one is Oregon Water Quality Index. Fourth one is the Weighted Arithmetic Water Quality Index method. So coming to the National Sanitation Foundation Water Quality Index. So this is a usual water quality index method that is developed by the National Sanitation Foundation. So in this index, it uses 9 water quality parameters such as the temperature, pH, turbidity, fecal coliform, dissolved oxygen, biochemical oxygen demand, total phosphates, nitrates, and total solids. Okay, considering these 9 parameters, the data will be summarized into a form of a single number. Okay, so the formula they have used here to assess this water quality index, so that is sigma WI into QI. So based on that mathematical relation, they will going to calculate the water quality index in national foundation. So this is the rating they have given. So 90 to 100 rating, it is excellent. Then 70 to 90, it is good. 50 to 70, it is moderate. 25 to 50, bad. And 0 to 25, it is very bad. Okay, this is the explanations of the classification of type of water resource usage when the water quality index is in that particular range. Next is Canadian Council of Ministers of Environment Water Quality Index. So here, this CCME WQI, it provides a very consistent method of calculating the water quality index, which is mainly formulated by Canadian Council of Ministers of Environment. So here this index is combinations of 3 factors, okay, not the parameters, 3 factors, where F1, F2 and F3 are the 3 factors. F1 represents the number of variable whose objectives are not met, whereas F2 represents the frequency with which the objectives are not met, and F3 represent the amount by which the objectives are not met. Okay, so considering these F1 can be calculated, the number of failed variable divided by the total number of variables into 100. F2 is number of failed tests divided by the total number of tests into 100, and the test value which are not exceeding the test objectives are considered as excursion. So depending on the ith parameter, we can able to calculate this excursion value. So failed test value divided by the objective minus 1. So similarly, the test value not falling below the objective can be calculated. So again, the excursion I will be equal to the objective I divided by the failed test value I minus 1. Okay. So based on these excursions, we can calculate the NSC. So NSC is the cumulative of the excursion divided by the number of tests, and F3 we can calculate based on this NSC. NSC divided by 0.01 NSC plus 0.01 into 100. Okay, so this mathematical relation can be used to calculate the F3. So then the water quality index of CCME is equals to 100 minus F1 square plus F2 square plus F3 square whole to the power of half, or we can say square root of F1 square plus F2 square plus F3 square divided by 1.732. Okay, this is the relation used to calculate the water quality index in CCME model. And this is the rating of CCME WQI. 95 to 100, it is excellent. So this is the characterization of water when the water quality index is in that particular range. And then 80 to 94, it is good. And 65 to 79, it is fair. And 44 to 64, it is marginal. So that means the water quality is frequently endangered and the conditions very often deviate from the natural levels. Okay, that's what when the water quality index is in this particular range. And if it is 0 to 44, poor, that means the water quality is almost endangered and the conditions are like regularly deviated from the natural levels. So next, the third one is Oregon Water Quality Index. This Oregon Water Quality Index creates a score to evaluate the general water quality of the Oregon stream. Okay, here the parameters that are considered are temperature, dissolved oxygen, biochemical oxygen demand, pH, ammonia, nitrate, nitrogen, total phosphorus, total solids, and the fecal coliform. Okay, so this model, Oregon water quality model, is designed based on the Delphi method. So in this method, water quality index, it employs the harmonic averaging to give the ratings. Okay, so ratings are given as when the water quality index is less than 60, it is considered as very poor. 60 to 79, it is considered as poor. Then 80 to 84, it is considered as fair, and 85 to 89, it is considered as good, and 90 to 100, it is considered as the excellent. Okay, so that is about the Oregon Water Quality Index. So coming to the fourth one, that is the weighted arithmetic water quality index method. So this method is classified the water quality according to the degree of purity by which most commonly measured water quality variables are considered. So this method is widely used by most of the researchers or the scientists while calculating the WQI. So the formula is of weighted arithmetic WQI method is sigma Wn into Qn divided by sigma Wn, where Wn is equal to K by Sn. Sn is the standard permissible value of the nth parameter. Okay, whatever the number of parameters that we are considering, so we need to consider the standard value of that particular nth parameters, and Qn will be equals to 100 into Vn minus Vio divided by Sn minus Vio, where Vn is the estimated value of the nth parameters, whatever that we have measured, and VIO is the ideal value of that nth parameter in the purest form. Okay, so based on this, we can calculate the Qn, and the K will be equals to 1 by sigma Si. Okay, where the I value will going to consider depending on the number of parameters. So I value will vary from 1 to n. So Si is the standard permissible for the nth parameter. So based on this formula, whatever the parameters that we consider, we can calculate the WQI based on the weighted arithmetic method. So here the rating they have given 0 to 25 is considered as, okay, it is almost the reverse of the previous other three W water quality index. So here it will start with the 0 to 25, it is considered as the excellent water quality, and 26 to 50 good water quality, 51 to 75 poor water quality, 76 to 100 very poor water quality, and the more than 100, which we can say it is unsuitable for the drinking purpose. Okay, once it exceeds the 100, it is considered as unsuitable or unsafe to use that water. Okay, so this is about the water quality index. So next we will going to start with the water treatment. So before we know about the water treatment, let us know what are the objectives of treating the water or goals of treating the water. So first and the foremost thing, we to remove the color, dissolved gases and the cloudiness that is present in the water, we will be providing the treatment. Then to remove the objectionable tastes and odor, then to remove the disease producing microorganism so that we can make that water safe for drinking, and to remove the hardness of water, then to make it suitable for a wide variety of the industrial purposes, because based on the type of the industry, the quality of the water that we need to supply will going to vary. Okay, to make it suitable for the industrial process, we have to provide the treatment to the water. Okay, this is the generalized flow chart of the water treatment, where the initially raw water will be taken to the first through the screens, will be taken to the aeration units. Then the alum, that is nothing but the coagulant, is added, flocculation tank, next the sedimentation tank, then it will be taken to the filters, and then it will be taken to disinfection, and then further it will be supplied to the public. So depending on, we may have to go for the storage. Okay, so this is again a flow sheet which shows the different unit operations and the unit processes that are used in the water treatment. So starting from the screens which are present in the intake structures, then when we come to the treatment, then it will start with the aeration, sedimentation with or without coagulation. So that depends on the quality of the water that we are taking. And next comes the filtration, disinfection, and then the miscellaneous purposes, or we can say the miscellaneous treatment. So depending on the purpose for which we need to supply, based on that we have to provide, other than the conventional treatment, we need to provide some additional treatment methods to that water, so that are referred as the miscellaneous. Then we can go for the distribution. So coming to the treatment methodologies. So in generally, the water treatment methodologies are classified as unit operations and unit processes. Okay, unit operations are those treatment methods where the physical forces will going to predominate. Okay, so the treatment methods where the physical process will predominate, so we can say those treatment methods as the unit operations. Whereas the unit processes are those treatment methods where there will be chemical or the biological process takes place, or addition of the chemical or addition of some biological organisms will going to bring out the treatment in the water. So then those treatment methods are referred as unit processes. Okay, so in generally or broadly, we can classify the treatment methods as unit operations and unit processes. Now, let us know what are the water treatment methodologies that are adopted. So, screening, aeration, sedimentation with or without coagulation, filtration, and the disinfection. Okay, these are the conventional treatment methodology that are adopted in almost all water treatment plant before supply to the public. So, we will discuss about these methodologies in detail one by one. Starting with, okay, before that, this is one question from one of the previous year gate paper. Potable water is prepared from turbid surface water by adopting the following treatment sequence. Okay, they are asking us the treatment sequence. What will be the treatment sequence? So the options they have given are, the first one is turbid surface water, coagulation, flocculation, sedimentation, filtration, disinfection, storage, and supply. Then the second option is turbid surface water, disinfection, flocculation, sedimentation, filtration, coagulation, storage, and supply. Then turbid surface water, filtration, sedimentation, disinfection, flocculation, coagulation, storage, and supply. And the fourth option they have given as turbid surface water, sedimentation, flocculation, coagulation, disinfection, filtration, and storage, and the supply. Okay, so in these four options, the correct option is option A, because the turbid surface water, this is the sequence that treatment that we are going to provide for to remove the turbidity or other impurities. So first we need to add the coagulant, okay, that we call as the coagulation. Then the once the coagulation takes place, then we have to remove those suspended solids, we have to do the flocculation, and then we will go for the sedimentation. And in the sedimentation, whatever the bigger size flocks are removed, whereas the supernatant will be taken to the filtration unit using the various types of filters. We will going to remove that fine suspensions, flocks which are in the suspension, and then after the filtration we will go for the disinfection. Okay, so this is the last phase of the treatment, water treatment. So after the disinfection, then it can be stored and then supplied to the public. Okay, so this is the correct sequence of the water treatment. So coming to the first treatment methodology that we are discussing is aeration. So this is one of the unit operation where the gas transfer will takes place, and it is very much important to exchange the gases between the atmosphere and water. Okay, so the objective of aeration is mainly to remove the taste and odor, to increase the dissolved oxygen content of the water to impart the freshness, and to remove the hydrogen sulfide. And also, once the hydrogen sulfide is removed, odor can be removed, because in the last class we have discussed that hydrogen sulfide will going to impart the rotten egg smell to the water. So removal of the hydrogen sulfide, we can able to remove the odor. So similarly, we can decreases the carbon dioxide concentration and increases the pH value, and we can remove the iron and manganese from the soluble state to insoluble state. And also this aeration can be used as one of the process by which we can able to mix the chemical with the water. Okay, so these are the sketches which shows the exchange of the gases from the water bubble, or we can say from the liquid to the gas. Okay, here in the first sketch, where we have considered a air bubble which is surrounding the water. Okay, so in this I have shown that the saturated value is very less than the whatever the concentration of the DO that is present in that gas. Okay, that means the saturation value is already it is considered it is lesser value when compared with the actual DO concentration of the gas. In such cases, what happens if the liquid surrounding that air bubble or the gas bubble is having lesser concentration of DO, then the gas will going to move from the gas phase to the liquid phase. Next comes the water absorption, when the saturation value is higher than the actual DO concentration. In that case, if the liquid from the liquid, it will going to absorb the oxygen. So this will going to happen as per the Henry's law. So factors that affects the exchange of the gases are the area of interface between the air and water, the thickness of the interlayers, and then the time of contact between the two films, then the partial pressure of the gas that is overlaying the atmosphere, degree of undersaturation or oversaturation of the gas in the water, are the important factors that has to be that will going to vary the dissolution of oxygen. Okay, so here let us know what are the important thing that we have to keep in mind to have a proper aeration. So first and foremost thing, we need to increase the area of water which is coming in contact with the air. Okay, so most of the time if the water is sprayed, then we are making that water into a smaller droplets so that we can increase the area of the contact of water with the gas. Okay, that is one thing that we can able to make to have proper aeration or increase the rate of aeration. And the second thing is to keep the surface of the liquid constantly agitated so that we can able to reduce the thickness of the liquid film. And when the thickness of the liquid film is less, so it will going to initiate or increases the rate of exchange of the gas. Okay, as we have the turbulence, so there will be mixing of water takes place within that body, and a thin layer of water will be coming every time, which can get exposed to the atmosphere and increases the rate of exchange. Then third point is to increase the time of contact of water droplet with the air, or to increase the time of flow of water. Okay, so if we allow the whatever the droplets to travel a longer distance in the air and then it will be collected, or we can make a water which is flowing in a thin film, we can make it to flow for a longer period of time before it reaches the next treatment unit. Okay, by this we can able to increase the time of contact between the water and the gas, and we can increase the rate of aeration. Okay, so the two important mechanism on which the aerators are classified are those forming the droplets or the thin sheets of water which are exposed to atmosphere. So that is one type of aerators are there. Then the second principle on which the aerators are designed is those forming small bubbles of air which rise in water. Okay, here nothing but uh, forming thin films or making exposing the thin films to atmosphere, one form, where fine droplets of air will going to rise within the water. Okay, here water will be brought in contact with the air in the form of thin film, whereas here in the second type the small air bubbles will be made to come in contact with the water. Okay, based on these two mechanisms the aerators are designed. Okay, the important types of aerators are, so free fall aerators, which are commonly referred as the gravity aerators. So we have four gravity aerators, that is cascade aerator, inclined apron aerator, slat tray aerator, gravel bed aerators. And then the other three types are spray aerator, mechanical aerator, and air diffusers or diffused aerators. Okay, so in these four types, in the water treatment plant, most commonly used is the gravity aerator, the two, the cascade type aerators, whereas others are they are majorly used in the wastewater treatment, not much in the water treatment. Okay, this is the cascade aerator. You can see the schematic representation of the cascade aerator, where the raw water will be made to pass over the number of steps in the form of a thin film. You can see here the water will be, when it is passing from one step to the another step, it will make to flow in the form of the thin film. Okay, as you can see in the picture also. So in this way we are making the water film exposed to the air, and we are, when we provide more number of steps, we are increasing the time of contact of whatever the liquid film to be coming in contact with the air. Okay, so the design criterias, you can just please remember, because they may ask some one or two question on this design criterias. So usually the number of steps that are provided is 4 to 6. The head requirement for this cascade cascade aerator is 0.5 to 3 meters, and the space required for this is 0.015 to 0.045 meter square per meter cube per hour. Okay, and the gas removal efficiency of this cascade aerator is 20 to 45% in case of the carbon dioxide, and 35% in case of the hydrogen sulfide. And this is the multiple tray aerators. Usually in this multiple tray aerator, coke or the waste ceramics are usually placed to increase the surface area of exposing the liquid film to the air. Okay, so here the size of the coke or the ceramic they are using will be 50 to 150 and the number of trays with the spacing, 4 to 9 trays are used. Usually the spacing they will going to provide 300 to 750 and the height of this multiple tray will be, maximum will be 3 meters, so it can vary from 1 to 3. And the space required for this multiple tray aerator is 0.013 to 0.042 meter square per meter cube per hour. And the gas removal efficiency in this case is 65 to 90% carbon dioxide can be removed, and 60 to 70% of the hydrogen sulfide can be removed, because here we are increasing the surface area of getting exposure of the liquid film to the air by providing the coke or the ceramic, waste ceramic of size 150 so that is going to increases the efficiency of this aerator. So next other type is spray aerators. As I told, mostly it is used in the wastewater treatment, not much used in the water treatment. So in this, the nozzle dia will going to vary from 10 to 40 and the nozzles will be spaced at interval of 0.5 to 1 meter, and the pressure head at the nozzle will be of about 7 meter. But actually, that is, with respect to theoretical, they say the pressure head required at the nozzle is 7 meter, but in practice, this value has varied from 2 to 9 meter. Okay, and the discharge rating per nozzle will be of about 18 to 36 meter cube per hour, and the area of the aerator 0.03 to 0.09 meter square per meter cube per hour, and the gas removal efficiency of carbon dioxide is 70 to 90%, and almost 90 to 99% is removed. Hydrogen sulfide is removed in this type of aerator. So that's why it is most commonly used in the wastewater treatment. And the time of exposure of the droplet, okay, they may give some data and ask you to calculate what may be the time of exposure of the droplet. So, okay, in that the most commonly used formula is T equals to 2 CV into square root of 2H by G into sin X, where H is the total head of water at the nozzle, CV is coefficient of velocity, X is the angle of inclination of the nozzle. Okay, considering that, we can able to calculate. Next, the fourth type of aerator, other aerators are the diffused aerators and the mechanical aerators. Since it is muchly used in the wastewater treatment, I won't be explaining much about these. Next, coming to the advantages of the aeration. So, with respect to the iron and manganese removal, so more than 0.3 milligram per liter iron will going to cause yellow to reddish brown color in the water, and also sometimes it will makes the stains over the plumbing fixtures. Okay, so that can be avoided when we provide the aeration. And if the concentration exceeds, iron and manganese concentration exceeds 1 milligram per liter, then the taste will be imparted, metallic taste will be imparted to the water, so that can be removed. And if the water contains both iron and manganese, the staining could vary from dark brown to black, so that depending on the concentration. And at the same time, in the aeration process, the water is saturated with the oxygen. Okay, then if it is saturated with the oxygen, then the oxidation products, ferric hydroxide and the manganese dioxide are insoluble, and after the aerations, so these can be removed by the clarification or other filtration process. Okay, so these are the advantages of aeration we will going to have with respect to the iron and manganese removal. Coming to the hydrogen sulfide removal, by hydrogen sulfide is removed by bubbling the water or by cascading. Okay, and then with this, the elemental, it will going to elemental sulfur will be released. So aeration will be most effective when the hydrogen sulfide is lower than 2 milligram per liter. Okay, not more than 2 milligram per liter. If it is less than, then we can effectively remove that using the aeration process. And the well designed the aeration tanks will going to maintain the pockets of air in the upper third or the upper half of the tank. Okay, so that will going to increases the efficiency. And if the tank does not maintain the air pockets in a correct proportion, then the sulfur odor may return back to that water, or it may get dissolved back in that water. Okay, so that is with respect to hydrogen sulfide removal. So coming to the limitations of aeration, so it is the unit operation of aeration which requires significant head of water, and then the water will be rendered more corrosive after aeration. That means more of oxygen is being dissolved in that water. When the DO is high, then the water will be more corrosive in nature, or the plumbing, whatever the plumbing fixtures that we are using, if it is made up of iron or steel, the chance of the corrosion is very, very high. So for removal of taste and odor, the aeration are not highly effective, but can be used in combination with the other adsorption techniques or other chlorine treatments. So additional lime may be required to neutralize the carbon dioxide that would be removed by the aeration. Okay, so these are the limitations that were observed when the aeration has been provided as one of the treatment methodology. So coming to the next method is the sedimentation. So it is the process of removal of the suspended particles through the gravitational settling. So here, depending on the usage of the chemical, we can classify as the plain sedimentation, and the other one is sedimentation with coagulation, where the chemical is being used in that treatment, or generally we call that as the clarification, or the treatment unit we call as the clarifiers. So the actually when we do the sedimentation process, it is the settling of the particles. So based on the nature of the particle that is present in that water body or the water column, the various types of settlings are being observed. So these are the four types of settling that is observed. One is the discrete settling, flocculent settling, hindered settling, compression settling, and as you have studied in the BE, that the sedimentation is mainly dependent on the Stokes law. Especially, it is more effective for the particles which are having a diameter less than 0.1 mm, and this is the settling velocity that we can able to calculate. So Vs equals to G into Gs minus 1 divided by 18V into D square, where Gs is the specific gravity of the solids, V is the kinematic viscosity. Okay, so this is the figure which shows the various types of the settling. So discrete settling, so most of the time the particles are in the suspended nature, and then the flocculant, when it starts to agglomerate to one each other in a smaller concentration, so that we call as the flocculant settling. Then as the concentration of the solids get increases, they will get attached to one another very easily, so that we call as the hindered settling. And at the bottom of the column, as the concentration of the settling of the particles get increases, it will going to get compressed, so that type of settling we call as the compressed settling. Okay, so this is the table which shows what type of particles will get settled, and where exactly these type of settling we will going to observe in the water and the wastewater treatment. I have just listed here. Next, coming to the types of sedimentation tank. So there are various types of sedimentation tanks that are used in the water treatment. So the important one, fill and draw type tank, okay, which schematic sketch I have shown here. So it is referred as the quiescent or intermittent sedimentation tank. Okay, here the water will be taken in a tank, and it will, that particular volume of water will be retained in the tank for some duration, and then after the specified time period, the water will be taken out of the tank through the outlet. Okay, so that's why the process will not be continuous in nature. It is referred as intermittent sedimentation tank, or that's why I call that as fill and draw type tank, draw type sedimentation tank. Okay, whereas the most commonly used is the continuous type tank, because in water treatment plant, water has to be treated continuously so that we can able to meet the public demand to supply the water. So in such cases we need the continuous type tank, so where water will going to enter at one end of the tank, and it will going to so that the entering water should not affect the outflow water. So the baffle valves will be provided, various number of baffle valves are provided, so that we can increase the time of travel of that water, and at the same time during this time of travel we can able to remove the whatever the particles, the suspended particles which have got flocculated or hindered, and it can settle, we can allow these particles to settle, and the sludge can be taken out from the bottom of that tank. Okay, the supernatant can be taken at the outlet which is provided at the top of that tank. Okay, so this type of tank, continuous type of tank, is most commonly used in the water treatment plant. So coming to the design aspects, okay, the important factors that affect the designing of the sedimentation tank are velocity of flow, capacity of the tank, inlet and the outlet arrangement, then shape of the tank, and the other miscellaneous considerations. Okay, these are the five aspects which will going to affect or which will be considered while designing the sedimentation tank. So coming to the velocity of flow, obviously, when the velocity of flow is slow, then the rate of settling of the particles will be high. Okay. Then coming to the most important design factor is the capacity of the tank. So capacity of the settling tanks are determined by the two method. Okay, one is based on the detention period, the other one is based on the overflow rate. So, how to find the detention period or what is detention period? Okay, it is the theoretical time taken by the particle of water to pass between the entry and exit of a settling tank. Okay, and this particular theoretical time we call as the detention period or the detention time. So to calculate the capacity of the tank, which is represented as C, so C equals to Q into T, where Q is the rate of flow of water per hour and T is the detention time in hours. Okay, so you know that the rate of flow usually we will be considering as meter cube per hour, and time will be detention time 1 hour or 2 hours or 3 hours, so depending on the whatever the concentration of the solids we will be taking. So when we multiply these two, we will going to get the capacity in terms of meter cube. Okay, so next is the overflow rate, so which is one of the important design parameter of the sedimentation tank. So this overflow rate is nothing but the quantity of water which is passing per unit hour per unit area of the settling tank. Okay, so it is also called as surface overflow rate, SOR, or we can also call that as just overflow rate. So we know that according to the previous relation, C equals to Q into T, we can simplify that relation and we can write that as T equals to C by Q, where C is the capacity of tank and Q is the flow rate. And we know that the capacity of the tank is nothing but length into breadth into depth of the tank divided by the flow rate. And we can also say the time t will be equals to the whatever the distance of the descent of the particle. Okay, because the suspended as in the sedimentation tank the particle will get settled, so what distance the particle has to descend, so that is considered here distance of the descent of the particle divided by the velocity of descent. Okay, so with this we can able to calculate the detention time. So here we can write t equals to d into d divided by v, so which we can also write that as side water depth divided by the surface overflow rate. Okay, so we already know that t is C by Q, and the second relation that we can have is side water depth by the surface overflow rate. So when we equate these two equation 1 and equation 2, so we simplify, we will get the surface overflow rate will be equal to V equals to Q by L into B. Okay, so that can this relation shows that the sedimentation of the particle is independent of the depth. Okay, it is independent of the depth. Okay, that is most important. So it is mainly dependent on the size of the particle. It is not dependent on the depth of the tank. It is mainly depends on the size of the particle. So for the plain sedimentation, okay, when they are not using any chemical, the whatever the surface overflow rate will be considered between 40 to 50 meter cube per meter square per hour, whereas for sedimentation with coagulation 50 to 60 meter cube per meter square hour is considered. Okay, the shapes of the tank that we can able to use in this sedimentation is rectangular tank with horizontal flow, circular tank with radial flow or spiral flow, hopper bottom tank with the vertical flow. Okay, so this is the rectangular tank rectangular sedimentation tank where the flow is horizontal, and this is the circular tank with the radial or the spiral flow, where at the center of that circular tank the inflow or the inlet will be provided, and that will going to flow on the either sides of the inlet. Next is the hopper bottom tank with the vertical flow. Okay, so where you can see here, so this is the inlet channel. The influent pipe will be made to flow in a downward direction, and the whatever there will be deflecting box. So as the particles move from the top of that bottom to the bottom of the tank, the particles will get settled, and the supernetted water will going to get into the draft channel, and from where the outlet will be water will be taken to the next treatment unit. Okay, so for the sludge, the outlet separate outlet arrangement will be made. So this is the hopper bottom tank with the vertical flow. So most of the time in the GATE previous year question paper, the most commonly asked questions are on, especially on the water treatment, sedimentation, flocculation, filtration, and disinfection. Okay, these are the four processes on which the most common questions are asked. So let me take up those questions, few questions. So first example, consider a primary sedimentation tank in a water treatment plant with the surface overflow rate as 40 meter cube per meter square day. Diameter of the spherical particle, which will have a 90% of theoretical removal efficiency in this tank, is how much they are asking. Okay, we need to calculate the diameter of the particle. Now, assuming the settling velocity of the particle in the water as described by the Stokes law, density of the water is 1000 kg per meter cube, and density of the particle is 2650 kg per meter cube, and the specific gravity is 9.81 meter per second square. Kinematic viscosity of water is 1.1 into 10 to the power of 6 minus 6 meter square per second. Okay, so now the options, they have given the four options, the values. So we need to calculate and say which is the correct answer. So as per our calculation, the correct answer is B, that is 22.58. So here we need to use the relation percent removal equals to Vs dash by Vs into 100. Okay, and here they have given that the diameter of the spherical particle, which will have a 90% theoretical removal efficiency as 90%. So we can simplify that and write Vs dash is equal to 0.9 Vs. Okay, and the Vs is nothing but the surface overflow rate that they have given, 40 meter cube per meter square day. So that I will be converting in terms of per second. So by dividing the 40 by 86,400, I'm converting that to meter per second. So now this we can say the Vs will be equals to 1 by 18 into d square into g by mu into rho s minus rho w, where rho s is the specific density of the suspended solids, and rho w is the density of the water. By substituting all these values and simplifying for d, we will going to get the value of the diameter as 22.58 micrometer. Okay, so that is the answer that we will going to get in this example. The next one is, a water supply board is responsible for treating 1500 meter cube per day of water. A settling column analysis indicates that an overflow rate of 20 meter per day will produce the satisfactory removal for a depth of 3.1 meter, and it is decided to have two circular settling tanks in parallel. So the required diameter of the settling tank is dash. So that means we need to calculate the diameter of the settling tank, which is expressed in meters. So the options that are given are, one is 6.5, 9.61, 6.91, and 8.1. So as per our calculation, the correct answer is 6.91. Okay, how? Let us see. The total area of the sedimentation tank required is, we can say, we know the flow rate Q and we know the overflow rate. Okay, so we can write 1500, that is the flow rate, by the overflow rate is 20. So we will going to get the area that is required to treat that water. Okay, so it is 75 meters square. And in the problem they have said that it is decided to have two circular settling tanks. So the number of tanks that we need to provide is 2. So then the area of the each tank will be the area, that is 75 meters square by 2, that is 37.5 meters square. Okay, now we can calculate the diameter of that settling tank. We know that area will be equals to pi d square by 4. So based on that relation, when we simplify for d, we get square root of d into 4 by pi. So here d area is 37.5. So when we simplify, we will get the diameter as 6.91 meters. Okay. The next example is, the two identically sized primary sedimentation tank receive water for type 1 settling under the laminar flow conditions. Okay, so the surface overflow rate maintained in the two tanks are 30 meter square per meter, 30 meter cube per meter square day, and 15 meter cube per meter square day. Okay, the lowest diameter of the particle which shall be settled out completely under this surface overflow rate of 30 meter cube per meter square day are designated as D30 and D15 respectively. Okay, now they are asking us the ratio of D30 by D15 is how much. Okay, it is very simple. So as per our calculations, answer that we get is 1.41. So for type 1 settling, that means the discrete particles, it is the Stokes law that will going to obey the settling of the particles in that type 1 settling. So where Vs is directly proportional to the square of the diameter. Okay, so now I will take the ratios of the whatever the diameters that are here. So d square by d30, d square by d15 equals to 30 by 15, because they have given the surface overflow rates as 30 and 15. So 30 by 15 will be equals to 2. And the same, when we take out that squares, so we need to take the square root of 2 here. So square root of 2 will be equals to 1.41 is the ratio of D30 by D50. Okay, so like that we will be calculating. And most of the time, to increase the rate of settling of the particles, the sedimentation tanks are provided with the tube settlers or the laminar plates. Okay, so as you see in the sketch, when the water is made to pass the sedimentation tanks, so the inclined plates or the tubes will be provided in that sedimentation tank, so that whatever the solid particles that are present in that water, when it is rising slowly in that through that tubular plates or the laminar plates, then the solids particle will get settled over those tubes or the plates, and as the density of the particles get increases, so it will easily slide down that plate and it will be collected at the bottom of the tank. Okay, so you can see here the tube settlers or the laminar plates, the water flows up through these slanted tubes along the slanted plates. The flock settles out in the tubes and the plates, and it will going to drifts back down to the lower portion of the sedimentation tank. Okay, and clarified water will be coming out of those tubes or the plates, and then those clarified water will be taken to the next treatment unit. Okay, so this will be increasing the efficiency of the sedimentation tank. Tube settlers or the laminar plates will increases the efficiency of the sedimentation tank to the maximum extent. Next, coming to the constituents of the coagulation and the sedimentation plant, it is the feeding devices, mixing devices, flocculation tank, then the settling or sedimentation tank. So the coagulants are the chemicals that are used to destabilize the colloidal particles. The process of adding the coagulant is known as coagulation. So in this, the destabilization of colloidal and the fine particles will take place, and also the initial aggregation or the agglomeration of these destabilized particles takes place. So the common coagulants that are used are aluminum sulfate, chlorinated copperas, ferrous sulfate, lime, magnesium carbonate, and the sodium aluminate. The principle of coagulation, mainly the flock formation and the electric charges. These are the two important principles on which the coagulation process will going to happen. So during this process, the destabilization of the colloidal particles will happen due to the double layer compression of the colloidal particles, then the charge neutralization, as you can see the in the sketches. So there will be positive and negative charge which will get neutralized. Then the bridging will takes place between the particle and whatever the precipitate that is formed, and the colloidals will get entrapped in those whatever the precipitate that is formed. Okay, and this is, as you know, that the jar test apparatus, which is most commonly used in all the laboratories to assess the optimum dosage of the coagulant. Okay, so this is one problem. The surface water treatment operates round the clock with the flow rate of 35 meter cube per minute. The temperature of water is 15 degrees centigrade, and the jar test indicated an alum dosage of 25 milligram per liter with flocculation at a GT value of 4 into 10 to the power of 4, producing the optimal results. And the alum quantity that is required for 30 days of the operation of that water treatment plant, we need to calculate. Okay, here to calculate that, we have to know the whatever the optimum dose. Okay, according to this data, they have said that 25 milligram per liter, and the flow rate is important, 35 meter cube per minute. So the options they have given, the correct answer is 37,800. Okay, let us know what is this kg or mg. Now we know the flow rate 35 meter cube per minute. So that I will be converting to meter cube per day by multiplying 60 and 24. And we know the alum dosage as 25 milligram per liter. So usually the dosages of any or the quantity that are required will be calculated in terms of kgs. So now to calculate the alum quantity for 30 days, we will be multiplying the flow rate in terms of day, meter cube per day, into the whatever the alum dosage that is required, 25, that we are converting into kg by multiplying 10 to the power of minus 6. Okay, so then 30 is the number of days in a month. Okay, when we simplify this, we will going to get the answer. The answer is 37,800 kg is the answer. That is the total quantity of alum required in that water treatment plant to treat the water. Okay, so next is feeding the coagulants. Okay, there are two types of feeding, dry feeding and wet feeding. You can just remember that you have studied in your sixth semester courses. So there will be wet feeding, which will be operated with the help of the rock and pinion arrangement. So the solution will be made, and it will be collected or stored in a tank, and then depending on the dosage, so they will going to make the arrangement to allow the flow of the whatever the alum solution or the coagulant solution to the water in a mixing channel. Okay, whereas in case of the dry feeding, either toothed wheel will be used, or the helical screw will be used to add the coagulant in the form of dry powder. Even the compressed air and the hydraulic jump method, mixing channel, and the mixing basins or other mechanical means are used to mix the coagulant with the water. So next process is the flocculation. So where the it is a tank where the flocculation process takes place. We call as the flocculator. The gentle agitation of the aggregates to destabilize the particles and to form the flocks, we call that tank as the flocculator. So according to the various researchers, the power required in terms of the watts we can calculate for the flocculator, because it has to run flocculator has to run slowly. So we will be using this relation P equals to half CD into rho into AP into VR, where and another relation that is G equals to square root of P divided by mu V. Okay, these two relations we can use to calculate the power requirement for the flocculator, where G stands for the mean velocity gradient and V stands for the flocculator volume and mu stands for the absolute viscosity. VR stands for relative velocity of the paddles, AP area of the paddles, and CD is the coefficient of drag of the paddles. Okay, so these are the design criterias of the flocculator. You can please keep these points in the mind, because they may ask the multiple choice what may be the depth of the flocculation tank or the range of the depth of the flocculation tank. Okay, so 3 to 4.5 is the depth. Detention time will be 10 to 40 minutes, and the velocity flow 0.2 to 0.8 meter per second, and the total area of the paddles 10 to 25%. Then the peripheral velocity of the blades will be 0.2 to zero point 0.6 meter per second. Gradient, velocity gradient will be 10 to 75 per second, and GT value will vary from 10 to the power of 4 to 10 to the power of 5, and the power consumptions will vary from 10 to 36 kilowatts per mld of water. Outlet velocity 0.15 to 0.25 meter per second. CD is, that is the drag coefficient, 1.8. Then the distance between the paddle edge and the side of the basin will be about 15 to 40 centimeter, and the K value is 0.25. The relative velocity is 75% of the paddle velocity. Area of the paddles will be equal to length of the blades into width into the number of blades in that compartment, and the distance between the two paddles in the same compartment, usually it will be about 1 meter. Okay, please remember these relations, so that in case of any short problems you can just use those relations. Okay, one problem or most commonly asked problem on the flocculation is calculating the power requirement. So a flocculator tank contains 1,800 meter cube of water, which is mixed using the paddles at an average velocity gradient of 100 per second. The water temperature and the corresponding dynamic viscosity is 30 degree and 0.798 into 10 to the power of -3 Newton second per meter square. The theoretical power required we calculate using the relation P equals to mu V into G square. By substituting those values, that is the dynamic viscosity, and then whatever the volume of the tank and the G value, we can calculate the power. So with that we will going to come get in terms of Newton meter per second, that can be converted to kilowatt. So we get 14.36 kilowatt. So coming to the next treatment method is the filtration. So it is the process of passing the water through the beds of sand, we call as filtration. The most commonly used filters are the slow sand filter and the rapid sand filter. So the third type of filter which is used in the swimming pools is the pressure filter. The principle involved in the, or we can say the mechanism of the filtration, it involves the three important processes. One is mechanical straining, then the flocculation sedimentation, biological metabolism, and the electrolytic changes. So as you see here in this sketch, mechanical straining means when the particle is passed through the filter at the top of the filter media, the particles will get held up because of its size. So that process we call as the mechanical screening. But when it enters, even though there are very fine particles or the smaller size particles that may enter the filter bed, so as you see in this sketch, it may whatever the smaller particles which entered the filter media, there will be small voids which are present in that filter media, so that will get sedimented or get clogged in those voids. Okay, that process we call as the flocculation and sedimentation. And at the same time, as when we filter the water continuously, there will be a slime layer or the microbial film that will going to form over the filter media. So that will also oxidizes the whatever the organic impurities that are present in that water, and the even fine suspended particles which are colloidal in nature. So since the sand particles are positively charged, those electric charges will get neutralized. Colloidal particles will get neutralized when it passes through the filter bed. Okay, so these are the four process that takes place during the filtration. And the sand that is being used as a filter material should be free from the dirt, should be uniform in nature and size, hard and resistant, and should not lose more than 5% of its weight after being placed in the hydrochloric acid for 24 hours. And the density, it should be of about 1600 kg per meter cube. Okay, and other than the sand, anthraphyllt and anthracites are used. So the types of the filters based on the rate of filtration, we have the slow sand filter, rapid sand filter, and pressure filters. So based on the gravity or the pressure, we can say gravity filters, where we will going to pass the water under the gravitational force. So that is slow sand filter and the rapid sand filters. But under the pressure, we will going to pass the water in the filter media. That type of filter we call as the pressure filters. Okay, so this is the construction of the slow sand filter, which consists of the enclosure tank, then the filter media, where you can please remember the effective size of the sand used in the slow sand filter is 0.2 to 0.4, and the uniformity coefficient of the sand should be 0.8 or 2.5 to 3. So finer the sand in the slow sand filter, the efficiency will be higher. Okay, so the base material used in this slow sand filter, its size will graded or laid in the layers of about 150 and the depth of that base material will going to vary from 300 to 750 depth. Okay, these are the specifications of the size and the depth of the layers. Okay, topmost zero point 0.2 to zero point 0.4 size, and the intermediate 0.6 to 2 and 2 to 40, and the lowermost will be 40 to 65. And this is the plan of the slow sand filter. And the filter head is limited to 0.7 to 1.2. The cleaning of the slow sand filter is not done easily as we can do in the rapid sand filter. So in this case, scrapping at the topmost layer, about 1.5 to 3 centimeter layer will be scrapped out if we want to clean that filter media. And whatever the microbial film that is formed in the slow sand filter is referred as Schmidt's decay, or in common we call that as the dirty skin. And the rate of filtration of the slow sand filter is about 100 to 200 liters per hour per meter square, and the slow sand filter efficiency is 90 to 99%. So this is the rapid sand filter. Okay, as you know, the important feature of this rapid sand filter is where we can able to give the back washing can be done. Okay, and in this, the enclosure tank will consist of the depth of the tank will be of about 2.5 to 3.5, and the area is 10 to 80 meters square. And to calculate the number of filter units that is required, the most commonly used empirical relation is Morrell and Valence equation. N is 0.112 into root Q. N is the number of filter units and Q is the treatment plant capacity in MLD. Then the filter media that are being used is 60 to 90 depth of sand layers are used. Effective size of that sand is 0.35 to 0.55 and the uniformity coefficient is 1.3 to 1.7. Okay, this is the specification of the base material that is required. And the under drainage of the rapid sand filter, the main objective is to collect the filtered water uniformly and also to provide a uniform distribution of the backwash water without disturbing or upsetting the sand layer that is present above that under drainage. Okay, so for that purpose, this under drainage system is provided in the rapid sand filter. So these are the other apprentices that are provided in the rapid sand filter. Wash water troughs to collect the backwash water, air compressor to pressure to pass the air during the backwashing, and the flow control devices. Okay. So coming to the remedial measures, because there are some operational problems that we will be observing in the rapid sand filter. So for that, to avoid those problems, by avoiding the development of excessive negative head. So loss of head should be restricted to about 2.5 to 3.5 meter. Negative head should be maximum of about 1.2, not more than that. Then controlling the growth of algae by remedying conditions that supersaturate the water with air, and by taking the precautionary measures so that the water should not get warmed as it passes through the treatment plant. Okay, precautionary measures will going to help in overcoming the remedial problems. Okay, so backwashing, when we want to talk, so please keep in mind that for the backwashing, about 2 to 4% of the filtered water is used. Okay, 2 to 4% of the filtered water is used. Okay, this is a schematic representation how the backwashing will be done. So the backwash valve will be open, and initially the water will be allowed along with the air. Okay, so air will be also passed. So air bubbles will going to come at the top initially, and then the water will be allowed to come up, and it will be collected in the backwash troughs. Okay, so here I don't want to explain once again this because you have already studied in your earlier classes. The air is blowed at the rate of 1 to 1.5 meter cube free air per minute per meter square of that bed area. Okay. So coming to the problem, a water treatment plant of capacity 1 meter cube per second has a filter box of dimension 6 by 10 meter. So loading rate to the filter is 120 meter cube per day, meter square. When 2 of the filters are out of service for backwashing, what is the loading rate we need to calculate? Okay, the options they have given are 4 options. So in this, correct answer is 144. Okay, here the total quantity of water filtration per day is, so we know 1 meter cube per second they have given, so that we need to convert to meter cube per day by multiplying 24 into 3600, and the surface area loading rate of the filters is given. So surface area we can calculate the quantity of water divided by the loading rate. So we got the area as 720 meters square. So area of the one filter, according to the whatever the dimensions they have given, 6 into 10, that is 60 meters square. So the total number of filters, 720 divided by 60. So 12 filters have to be needed. But according to the whatever the data they say, the 2 filters are kept for out of service or during the backwashing. Okay, so 2 will be out of service, so that means totally 10 filters has to be operated at in that treatment plant. So the surface area will be that is needed is 60 meter square is the one area of the filter, then 10 filters will be 600 meters square. Then the loading rate will be whatever the total quantity of water that is being treated divided by the area. So we will get 144 meter cube per day per meter square. Okay. So similarly, another problem, a rapid sand filter comprises a number of filter beds is required to produce 99 mld of potable water, and it is considered water loss during the backwashing is about 5%. The rate of filtration is 6 meter per hour, and the length of the width ratio to the filter bed is 1.35, and the width of each filter bed is to be kept equal to 5.2 meter. One additional filter bed is to be provided to take care of the breakdown, repair, and the maintenance. So total number of filter that is required will be how much they are asking. Okay, so options, the 4 options, the correct answer is C21. Okay, so how to calculate that? Total water to be filtered is 99 mld, and they have given that consider the water loss during the backwashing as the 5%. So considering that 5%, we are multiplying this 1.05. So the total water to be filtered is 1.03.95. Then length to breadth ratio is 1.35 they have given, and also given the width as 5.2 meter. So based on this, the length will be 7.02. So the surface area of the each filter, the length into breadth, we get 36.05. The total surface area required will be equal to discharge through the filter by the rate of filtration. So we get as 721.875. The total number of working units that is required will be 721.85 divided by the area of the each filter. So we get around 19.77. Okay, that we can round up as 20 filter. So one filter is to added as the standby. Then totally 21 filters are needed. Okay, so this is the comparison of the slow sand filter and the rapid sand filter. And the pressure filter, so this is the type of filter which is used in the swimming pools where the rate of filtration is very high, and here it is passed under pressure about 300 to 700 kilonewton per meter square. Okay, I think diameter 1.3 to 1.5 to 3 meters, and height will be 3.5 to 8 meters. So here I can say it is very easily cleaned. Again, it will be done under the pressure. The rate of filtration is 6,000 to 15,000 liters square. The efficiency is less efficient than the rapid sand filter. Okay. So coming to the disinfection, it is the process of killing of the pathogenic organisms. Okay, here the substance, a chemical will be added to kill the microorganisms. Okay, that substance we call as the disinfectant. So the good requirement of the disinfectant, it should leave the residual concentration, it should be obtained it should obtain the harmless water after the treatment, and also economical, easily available, unobjectionable, and strength can be quickly determined. Okay, then the no skilled personnel is required and no other costly equipment is needed for this, and the reasonable time it should be able to react. Okay, the various methods of disinfection are physical methods by heat. Okay, and the other chemical methods are oxidizing agents, metal ions, and then the alkalis, acids, and the surface active chemicals. Okay, I don't want to deal with these minor methods of disinfection. The most important or the commonly used method is the chlorination. And in this chlorination, the mechanism on which this disinfection depends is the damage to cell wall, alteration of cell permeability, changing the colloidal nature of the cell protoplasm, inactivation of the critical enzymes which are responsible for the metabolic activity in the uh, present in the cell wall of the microorganism. Okay, so coming to the disinfection kinetics. Okay, when a single unit of microorganism is exposed to a single unit of disinfectant, the reduction in the microbes follows the first order reaction. Okay, so that we can mathematically write as dn by dt equals to minus kn, and also we can simplify and write this as n equals to n naught e to the power of minus k into t. Okay, this equation we call as the Chick's law. Okay, where n is the number of microorganisms present, and n naught is the initial number of microorganisms that are present. K is the disinfection constant, which depends on the type of the disinfectant agent that we use, and T is the contact type. So the factors that affects the disinfection process are the type, condition, concentration, distribution of the organisms to be destroyed, type and concentration of the disinfectant, chemical and the physical characteristics of water to be treated, the contact time available for the disinfection, temperature of water. Okay, so this is the action of the chlorine. When the water reacts with the chlorine, okay, it needs the pH less than 5. Okay, during that time it will going to form the hydrochloric acid and the hypochlorous acid. So this hypochlorous acid is very unstable in nature, so this will further disintegrate to form hydrogen ion and the hypochlorite ion. Okay, so hypochlorous acid also have the disinfecting action, hypochlorite ion also have the disinfecting action, and chlorine also, elemental chlorine also has the disinfecting action. But only thing that we need to maintain the pH in these particular levels to have the concentrations of these forms of chlorine. Okay. Okay, the various forms of the chlorine, one is the hypochlorite, then the chloramine, chlorine dioxide, and the free chlorine gas, which we are using presently in the water treatment. Then the forms of chlorination, it is the how we will going to add the chlorine to the water, plain chlorination, pre-chlorination, that means before the treatment, after the treatment, post chlorination, double or multiple chlorination, breakpoint chlorination, super chlorination, and dechlorination. So actually this breakpoint chlorination we will going to use to decide the how much of chlorine dose has to be added to treat that particular water body. Okay, so based on how much of chlorine demand is that we can able to assess using this breakpoint chlorination. The tests that are conducted to assess the residual chlorine is orthotoluidine test, DPD test, that is diethylene paraphenylene diamine test, chlorotex test, and starch iodide test. Okay, they may ask this as a multiple choice question. So in this disinfection also, most of the time they will be asking the whatever the chlorine dose, what amount or the quantity of the chlorine that is required in treatment of the water. So one such problem is water purification works handles 50,000 meter cube per day of water and consumes 20 kg per day of the chlorine. The residual chlorine after 15 minutes of contact time is 0.2 milligram per liter. So dash is the chlorine dose used in the treatment we need to assess. Okay. So for this, the out of this four option, the correct answer is B, that is 0.6 milligram per liter. So how we will know here? So water chlorine demand will be equals to 20 kg per day chlorine is needed. So we are converting that kg to milligram by multiplying 10 to the power of 6 and dividing the quantity of water that we are treating by meter cube per day. We are converting it to liter per day. Okay, so that we can get as milligram per liter. So according to that, the chlorine demand of that water is 0.4 milligram per liter. And in the data, they have said that the residual chlorine that it will going to give is 0.2 milligram per liter. So we know the chlorine dose is chlorine demand plus the residual chlorine. So 0.6 milligram per liter of dosage we need to use. Then the next problem is the chlorine is used as the disinfectant in the municipal water treatment plant. It achieves 50% of the disinfection efficiency measured in terms of killing the microorganisms in 3 minutes. So 99% disinfection efficiency is achieved. So what is the time period in which it is achieved? We need to calculate. Okay. So for that, we will be using the kinetic relation. Efficiency equals to N naught minus NT by N naught. So we know the efficiency is 50%. So then we can write these relations. N naught minus N naught into e to the power of minus kT divided by N naught is 1 minus e to the power of kT. So that we can simplify and write that as minus kT equals to natural log of 0.5. So we get the k value as, since we don't know the whatever the constant, we can calculate the constant as 0.231. Then based on that, we know 99% disinfection efficiency is achieved. So we need to calculate the time period. So we have calculated the k value as 0.231. So using this relation, we can calculate the t. So t value we will going to get as 19.93 minutes. Okay. So that is the answer D. The next another problem, the similar problem where we will be calculating based on the kinetic relation. So here we will be calculating the whatever the length of a particular length of the tank in which the disinfection process is being taking place. Okay. So I hope the miscellaneous last part of the water treatment, where we will be using the adsorption process to control the taste and odor, color removal, and also most of the time to increase the surface area while providing the treatment, we will be using this adsorption process in the form of the granular and the powder forms. Okay. So this granular activated carbon have the surface area of about 500 to 1400 meters square per gram. And this is the principle of the adsorption process. And this is the granular activated carbon, which is being used as the filter media in miscellaneous treatment to remove the odor or the color which may be present in the water. Okay. And then most common technique, miscellaneous technique is in while supplying water, fluoridation, where we need to add the fluorine so that we can have the concentration between 1 to 1.5. So for this, the compounds we are using is sodium fluoride, sodium silicofluoride, hydrosilicic acid. And then while providing the treatment, we may also need to have remove the fluoride, because whenever it is present in excess, so defluoridation has to be done when the fluoride concentration is more than 1.5 ppm. So the process of reducing the fluoride concentration is defluoridation. So the method that are used in the defluoridation are use of calcium phosphate, bone charcoal, synthetic tricalcium phosphate, ion exchange, lime, aluminium compound, and activated carbon. But the most famous technique is the Nelagonda technique, where the alum with the alum and lime is added to the water. So during that process, whatever the aluminium sulfate will be get precipitated with the fluoride to form the aluminium fluoride complex. Okay. And the lime will going to initiate that particular will going to maintain that chemical reaction in the presence of the lime. Okay. For that purpose, alum and lime is added. That technique is popularly referred as Nelagonda technique. Okay. So with this, we can able to treat the water to the maximum extent. Okay. I hope you have benefited from the whatever the treatment methodologies that I have explained, conventional and the miscellaneous treatment that can be provided to the water. Okay. Over to Manoj sir.
Thank you, ma'am. Thank you for a very informative session. Hope the participants have understood the concepts explained by Dr. Shilpa madam. Next session is at 3:45 by Professor D.P. Mahesh sir on fluid mechanics and hydraulics. Stay tuned. We'll meet you at 3:45. Thank you.